Mm, let's continue. So last time we were talking about Fourier analysis. Ooh. Okay, we started from Fourier series. Okay, we say any periodic function with a 2 pi period can be rewritten into this form. Hmm. Okay, or if you think about everything in terms of linear algebra, basically we're just trying to say, okay, any vector, which is a function, can be rewritten as a linear combination of all sine nx and cosine nx and constant. So naturally, sine x, sine 2x, dot, 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 cosine x, cosine 2x, and finally a constant forms a orthogonal basis. Okay, of or 2 pi period functions. Okay, so that's the first thing we did. We say, well, anytime you see a wave, you can decompose it into multiple waves. Anything that repeats itself, it basically, its foundation, its origin is nothing but a lot of periodic function added together. Okay, then we extend the idea from 2 pi to L, any L periodic. Okay, and then instead of sine nx, we do sine 2 pi n divided by Lx, and we do cosine 2 pi n over Lx. It's just a variation by shifting, by shrinking or stretching the whole thing. Basically, it's just a rescaling from 2 pi to L. Still good. And then we went from here to complex, because sine and cosine together, we can use another way to say it. That is going to be fx equals sum. We're going to use another one, which is ck. But this ck is nothing but related to the an and bn before. Okay, but this time you just have c. Meanwhile, you have I omega t. This omega is nothing but the frequency. Okay, take it back. I n t. This n is nothing but just the frequency of this. Okay, but this time it went from negative infinity to infinity. Meanwhile, it's complex. And finally, we say, well, we can extend it to continuous case. So finally, we have a Fourier analysis, a Fourier decomposition. That is fx roughly is going to be c. It's not k anymore. It's going to be c omega. Okay, e I omega t, d omega, because your omega doesn't have to be an integer anymore. It can be any continuous thing. This c omega here will be the coefficients, and we call this one the Fourier transform. Of the original function. Full negative I omega t, yes. Let's use x. Usually we use t because it's a time domain. So yeah, I use t there. So let's use t. Okay, that will be the Fourier transform, which basically give you the coefficient of the waves of different frequency contained in the original function. So what you're trying to do is you're taking a function which is called ft. You're trying to probe it with negative I omega t with frequency I, omega. Okay, this one either respond and say, well, we have a resonance. That means this one contains this frequency. Or this one respond 0, which means I do not contain this frequency in my original signal. Okay, you only have 2 possible choices. Now, what we can do is we can do some application. I want to share the desktop. Just keep in mind, yes, desktop. Okay. Last time we kind of did this. We said, if we have a signal, did I forget to close the one? Yes, I forgot to close the one. Okay. Either way. If you have a signal, you sample it, and then you use Fourier transform, you can actually decompose the original signal, okay, into 3 sine curves. From here, what we see here is like you have a sine 13, you have a sine 50, you have a sine 120. Okay, so seeing any combination of signals, you will be able to actually go back and try to see where the original signal come from. That means if you have 20 people, okay, speaking in the classroom, what you end up having is actually all the 20 sound with different frequencies got merged together into one signal. But once you take this signal, okay, from that thing and assume everybody speak at a very different frequency, okay, you will be able to redecompose everybody's voice, okay, compared to just receiving all the noises together. That would be super cool. Now, of course, in real life, this is never the case. In real life, we always have noise coming from the background, coming from, even when you speak, you cannot maintain a steady frequency. So what you really receive in real life is something like this. Here. What did I do? I did everything correctly. Do it again. F. $45. Plot. Shit, I deleted. Now I need to figure out what I deleted. I have the Fourier. I have the single. Let's change it to Y. If this one doesn't work, I may delete it a block. It will take me a while to figure out what's going on. Yeah, can't do that. Okay. Did we show the example last time when you have the noise? You just deleted the noise? Okay. Probably go back to that. It's exactly the same thing, but somehow I deleted some of the stuff. Okay. Now here's another application which we want to talk about. You can do it for any signal. So last time I showed you some sound or vibration from the air. This time we can do pictures. Okay, so this is what I got. I got it from a website, a picture of Iron Man. What I did is actually I just add a lot of noise to this picture. So imagine you get it from a security camera with a lot of disturbance. So the real picture you receive will be something like this. Okay. Now you can see if you do the Fourier analysis, but this time it's going to be 2-dimensional Fourier analysis. You have an X direction wave, you have a Y direction wave with different frequencies. Okay. Still, you have their magnitude. This one basically means you have a lot of low frequency waves, but the rest of the thing is basically just 0 or very small. So there are the noise. What I can do is I can go into the noise. I can make everything that is a little bit bigger than 0, but not big enough to be 0. So I deleted every noise which has high frequency in X and Y direction. Then I put all the signal back. Just as I put the signal back in the sound wave, I got a reconstructed picture. And from here you can see Now you can roughly see it's an Iron Man, right? Okay, so this is noise canceling, not in sound, but this time in pictures. Of course, you can increase the threshold and decrease the threshold and see how much you want to keep. This is to keep more frequencies. So you can see you retain most of the noise if you do things in this way. But if you do too few, that means you only keep a few frequencies. You can see the noise are basically removed. The sad thing is the useful signal are also removed. Okay, because you remove too much. You only keep the low frequency. The good thing is you still roughly maintain, you know, the rough, you can see, or you can already see the sine cosine curve here, right? Sometimes it's dark, sometimes it's bright. It's already like low frequency sine cosine curve here, okay? But you're really missing are actually the edges of those kind of pictures. You really want the edge of the Iron Man because the edge are really sharp if you look at this one. That already tells you the limitation of Fourier analysis. That is, it's not very good at doing sharp stuff. So let me show you the example. Here. Okay, first, let's take some signal. What I'm going to do is I'm going to take a Fourier analysis and then delete all the thing and then reconstruct everything using Fourier analysis. Fourier series, sorry. I'm going to use 1,000. Okay. It's hard for you to tell the difference, but there are two lines, a black one and a red one. The black one was the original signal. Okay. The white one is what I constructed using 1,000 sample points. From here, you can see it's almost perfect. Because your original signal was nice, it's a sine cosine wave. Now let's try something different. Let's try something which is not smooth. Well, this one is not smooth. As far as you can see, it's not like a curvy. You have a sharp corner here, you have a sharp corner here, and you have a sharp corner here. But by adding enough Fourier analysis, Fourier series, actually this is not a trouble for Fourier. Okay, even though your derivative is not nice, but as long as it's not too dramatic, it's fine. Now let's see what happens if we have a sharp edge. The red one will be the one you did for Fourier analysis, Fourier series. Do you see the problem now? This one has a sharp edge, sudden jump. The black one is the one you're trying to approximate. Okay. Now you can see Fourier actually does use a lot of sine and cosine waves putting together in order to approximate any functions. But for sharp things, you will always have those kind of oscillation at here, and it's not a small oscillation, it's a pretty big oscillation. What can you do? You can use more points. But from here, you can see even if you use more points, well, this is better than before. Still, it's pretty bad at the edge. Sounds good? Okay. That's a natural disadvantage of Fourier analysis. And if you think about it, it's not hard to see why. Think about a sine wave. Fourier is nothing but sine and cosine waves, right? Sine wave goes forever. Sine wave exists for everything from negative infinity to infinity. The amplitude stays the same. Okay? Then if you have something only exists for a small period, instead of existing forever, it's going to be really difficult for you to approximate something like this with the basis where each one of the bases exists forever for negative infinity to infinity. That's the difficulty here. So naturally, you have some improvement. We won't have too much time to talk about it. I just want to mention it quickly. That is called wavelet. So instead of using sine and cosine waves, this time what you can do is you can use this, something called a wavelet. Number one, this looks like sine cosine. Okay, you can actually have all those kind of signal vibrations you want. Meanwhile, you can see this one only exists for a small period. Very far away, very far away this direction, they are all zero. When you're close, you still have small amplitude. It's only big around a certain place. That will be some basis we can pick, which is called wavelet, and that will handle the sharp edge thing because the basis we pick is better than sine and cosine. All right. That will be everything about Fourier analysis and a little bit about wavelet, which is very, very useful. Originally, I was going to show you a wavelet decomposition of the Iron Man, okay? And that thing can actually filter out all the noise super nicely while keeping the sharp edge. The problem is I need to pay to get the package, so I decided not to do it. Okay, but if you have money, you can buy that package. I think it's $45. You can easily do the Iron Man thing. Okay, so basically, just think about it. You have something like this. You're trying to say this one is the sum of this, and this. Each one which goes forever. That's the Fourier series, right? It's going to be difficult. But what if you can have some sine curve, which is small, only big here, and then small again? Then this one, if you use a field of them, will be able to approximate something that happens locally. Here and here. Okay, that's basically the idea of wavelet. Of course, your job is still try to construct an orthogonal basis. The nice thing about sine and cosine is that they're orthogonal. Okay, so for wavelet, you need to be careful when you construct bases like that. But once you succeed, any function will be a linear combination of the wavelet function you just computed. Okay. Then it becomes the same as linear, as the Fourier series. All right. Fourier. Okay. Laplace. Let me write it down first. Okay. With that thing in mind, now you can see Laplace transform and Fourier transform are basically the same thing. Okay. There are only several differences, very small little tiny differences. Number one, you use omega I use S. Okay. Number two, you go from negative infinity to infinity, I go from 0 to infinity. This one doesn't have to be this way. Okay. We only pick this one because we want to solve ODE. Later, I will show you why. Okay, so this is later. We will show you why we pick 0, not infinity to negative infinity to infinity. Okay. Other than that, they're totally identical. Okay. From here, you can see the final thing goes from here. That is e to the a plus bi, which give you e to the a times e to the bi, which is cosine. Just e to the bi. And this one got expanded to cosine bi, cosine b, sorry. Plus I sine b. It all narrowed down to Euler's formula, and then you can see Fourier analysis actually handles this. We're talking about sine, cosine, we're talking about signals. So of course this is natural. Laplace transform handles the real part. That's the connection between these two. Okay. Some side topic, maybe later we can talk about it. Fourier analysis is very popular in solving partial differential equations. And Laplace is very popular for solving ordinary differential equations. So they can even solve the same thing. Not the same thing, but the same dynamical system, but it just one is partial differential equation and the other one is ordinary differential equation. That's where Laplace transform come from. Okay, so Fourier was trying to compare your function with sine and cosine. Laplace was trying to compare your function to e to the t exponentials. And if you recall what we did before in chapter 1, 2, 3, 4, everything we did was trying to treat the solution of a differential equation as an exponential, right? So naturally, Laplace transform is a good choice. All right, now let's see how do we use this to solve differential equations. Number one, definition of the transform. Okay, we call it ys. It's a function of s. We write L, we put a bracket, we put the function we want to transform in. That's the transform. Okay. It may look weird, but just think about this. Y1 is this. Okay, if you know y, you will be able to compute this one, and this one is going to be a number because it's an integral. It's a definite integral, right? Y2 is going to be this. So it's going to be a number once you know the s. From here, you can see ys is nothing but a function. If you put s in, you got a number. So it's a function of s. How do we compute it? We can try some example. Example 1, y equals 1. That's probably a very easy function. So what is ys? L y. 1 times e to the negative st dt. Okay. Do you know how to take the antiderivative of e to the negative st? That's this. Okay. You want to plug in 0. You want to plug in infinity, which you couldn't, but you can take the limit. Okay. This minus 1 over s, because if you plug in 0, of course you got 1 for the whole thing. This term is nice. Okay. What you should put here will be the limit of this one when t goes to infinity. Okay, so basically roughly you're looking at something like e to the negative st. And here is roughly negative s infinity with something called y over s. Sounds good? Does the limit exist? Yes, it's 0. If s is negative. Okay, it's like e to the negative 2 infinity, whatever. This is just e to the negative infinity, which is 0. Okay. What if s is positive? Oh, sorry, positive. Okay. What if s is negative? Then this one becomes positive, right? This one goes to infinity. Therefore, the limit does not exist. So this one's only defined for this, which is 1 over s. Okay, so I think I can write it down. Ly, your y is actually 1. Equals 2 possibilities. Does not exist if s is less than 0. Or 1 over s if s is bigger than 0. Okay. From now on, you will see this as very common. That is, if you do the integral, you will have an improper integral. You need to compute the limit at infinity. Okay. Certainly, sometimes it exists, sometimes it doesn't exist. Okay. So from now on, every time you write down something like this, you just write down when that thing exists. So you don't have to actually give me both cases. You can just simply write down this. So that will be the final answer for this. This is kind of unnecessary because everybody knows the agreement. That is, if I don't write it down, that means it does not exist if s is not bigger than 0. All right. Let's try another one. If I take my y to be e to the 2t, which can be a solution of my ODE, right, for some ODE, what's the Laplace transform of that? Okay, that's going to be e to the 2t times e to the negative st dt. Two minus st dt. Now again, I have this. Zero. A goes to infinity. No. A. Limit. A goes to infinity. Okay. Which is something minus 1 over 2 minus s. Here. Yes, 2 minus s. Okay. Here I should put 0. Okay. But you know, if you want to put it 0, that must mean 2 minus s should be negative. That means s is bigger than 2. If 2 minus s is positive, you plug in infinity, you got infinity. Does not converge. Sounds good? Okay. Then probably we can start to have a general conclusion. That is, this doesn't have to be 2, right? This can be anything. It can be any number you put here. I just changed to this. Still works. Still work. Yeah, A is a bad choice. Well, it's not a bad choice. Let's change this to be B. Okay. And then change this to be A. Okay, change this to be A and this to be A. So if you just repeat this one for e to the 3t, e to the 4t, e to the any t, we can have a general conclusion that is L e to the at should equals 1 over s minus a for s bigger than a. Sounds good? All right. That's two examples on how to compute Laplace transform. Now, if I give you any random thing, like can you find the Laplace transform of x squared plus x minus 1? Can you find Laplace transform of sin x? Or things like that. If you want, you can always go ahead and try to finish what you have here. Okay. You can imagine it's going to be a lot of integration by parts because you have two things multiplied together. And actually, people provided you a table. Okay, so you can actually find a table online. Since we're using all those kind of popular ones, people have computed for you. Okay, so you can have a fun table. That's the definition. We will use this one commonly. Now, number two. Of course, how does this help us to solve differential equations? We need to talk about properties of Laplace transform. Okay. The first one is quite easy. L is linear. That means L, CA, which letter do I want to use? There's no letter. So let's see, CF, AF, let's use AF. AF plus BG equals ALF plus BLG. It's a linear. That means what? That means the Laplace transform of this one can be decomposed into 3, Laplace transform of e to the 3t, plus the Laplace transform of 1, which can be 3 times 1 over s minus 3 plus 1 over s, given that s is bigger than 3. That means everything you learned before about linear algebra can be applied to this. You can talk about eigenvalues. You can talk about linear combinations. You can talk about all those kind of things because it's linear. That's great. Second, of course, why is it linear? It's not hard to see. If you have two functions, you want to do this. Okay. That's just the integration of this. Can you split them into two? By breaking the parentheses and split, the answer is yes, because integration is linear. Okay, so let's just write down one thing. This is linear because integration is linear. So we don't even have to prove. All right, linear. Second, probably the most important. For differential equation, we handle derivatives. So we probably want to know the Laplace transform of a derivative. That is going to be this with a prime. Okay, what's that? Well, that can be done by integration by parts. Okay, minus and according to integration by parts, this one should be replaced by the derivative of this. Okay, now let's clean things up a little bit. Number one, I want to move this one to the forward, to the front. Notice it's an integration with respect to t. That means you can treat s as a constant. That's why I put s in the front. And what is that? That is just the Laplace transform of the y without the derivative. Okay. What do I want to put here? I want to put what happens at infinity minus what happens at 0. So this term is pretty nice. I just want to put it here. Okay. What's the trouble? The trouble is this thing here. What can happen? It can be infinity, which makes the derivative does not exist. The Laplace transform of the derivative does not exist. Or this can be 0. Because this one decay like crazy. It's exponential decay. You times exponential decay by anything that is slower than exponential decay, eventually this one will go to 0. Sounds good? Okay, for the first case, we just say we give up. There's no Laplace transform. But for the second case, that's what we want. So now I think I can write down what's going on. I shouldn't call this infinity. I should call it junk. Okay, so basically L y prime actually equals S Ly minus y0. Okay. Provided that this goes to 0. Okay. In general, this is not hard to do, depending on what your y is. Okay, your y can be, sine and cosine. Your y can be polynomial. That's fine. Note what's going on here. You have this one. This one goes to 0. Okay, it goes to 0 at the speed of exponential. So as long as we can make sure what? Make sure, and this is a big assumption, yt is at most exponential. We will make this assumption through the chapter. So don't ask me like, what if this one fail? If this one fail, we need something else. For now, as long as I write it down, I'm already making this hidden assumption. For the whole chapter, I make this assumption. That is yt is at most exponential. Therefore, you multiply something at most exponential with exponential decay. When t goes to infinity, it will always be 0. Okay, so the assumption here is try to make sure everything I just write down is well defined. Of course, we need a careful definition. What do you mean by this? That means there is K M such that yt is less or equal than e to the mt. Okay. When t is bigger than k. This should be a small t. Okay. That basically means, for example, if your yt is e to the 2t, e to the 2t grow exponentially, right? Eventually, the limit is infinity. However, you multiply it by this. This is a monster. Okay, so no matter how big you are, as long as your t is big enough, you are going to go to 0. Okay, you can put a 20 here. Doesn't really matter. As long as you're finite, okay, or at the most finite, at the most exponential, okay, you will be canceled out. Sounds good? Okay. Second, what do you mean by t bigger than equal than k? That just means, you know, I'm trying to do this. I was trying to do that. Okay. And I'm telling you, you feel free to behave. Feel free to behave any weird. You can be e to the t square, which is way faster than e to the t exponential. As long as you only behave like this for t less or equal than 10. And after 10 or after 20, you start to behave like at the most exponential. I really don't care about the finite part. Okay, you can be crazy for an interval with a length of 200, but starting from there, you become well-behaving, you're still fine. Sounds good? So your function does not have to be well-behaved at the beginning. As long as eventually it starts to be well-behaving, this is also doable. Because anything that happens with finite interval, we really don't care. Okay. And I already write down something that can break this. For example, e to the t square, this is way faster than exponential. Okay, e to the t is even faster than this. Okay, so actually in general, there's a lot of functions which can be faster than exponential. That's not our concern for this chapter. Sounds good? With these two properties, we can already solve differential equation. Let's solve an easy one. Y prime equals to y, okay? Y0 equals 200. We know the answer. The answer is 200 times e to the 2t. That's the solution, right? But let's see how to solve it with Laplace transform. Okay, they're the same. Therefore, the Laplace transform of them are still be the same. All right. Ly prime, you know how to do this. This is SLY minus Y0, according to the thing we just computed, right? Here. That's the property of Laplace transform. Okay. On the right, you have L2Y. But remember, Laplace transform is linear, so you can take the 2 out, and this is Ly. They are the same, so let's move them all together. Y0, by the way, is 200, so let's just take 200. So Ly is 200 times 1 over s minus 2. Sounds good? Okay. To solve the differential equation, what's your job? Your job is try to find y, right? What did we just do? We found Ly. We know if we have the solution, we take the Laplace transform, it's going to be 200 times 1 over s minus 2. Good so far? Which function, if you take the Laplace transform, give you 1 over s minus 2? Check your notes. Does it look like this? Right? So if I want particularly 2, what I'm looking for e to the 2t. Okay, therefore y should equals e to the 2t. For this part, of course, I should have a 200 here. Okay, why? Because L e to the 2t is 1 over s minus 2. Therefore, if Ly equals 1 over s minus 2, y should be e to the 2t. That's the logic. Okay. Does everything make sense here? It's beautiful. Through the process, did you ever handle integration or derivative? No, you just handled algebra, right? Where did the derivative go? The derivative was here. But with this nice property, if you have a derivative, it's equal to not having the derivative, but adding an s and a minus y0. Sounds good? So next time you see a differential equation, what's going to happen? You're going to put a Laplace transform on that. Okay, after that, what will happen? Y prime will be gone. Y prime prime will be gone. Y prime prime prime, all of them will be gone, right? Leaving you only what? Leaving you only Ly. Still okay? If you have an equation, you have a lot of Ly. What do you mean by that? That means I have an equation, I have a lot of Ly. It's the same thing as I have a lot of equation with a lot of x. You just solve for Ly. But you solve for Ly using only algebra, no calculus. Sound good? When you finish, what's your answer? Your answer is going to be Ly equals something, because that's the whole thing you have, right? Now you need one more step. That is, once you know Ly, can you find y? Can you see that is naturally a question to ask? Do we have something called inverse Laplace transform? Make sense here? If I see e to the 2t, Laplace transform give me 1 over s minus 2. Great. If I see 1 over s minus 2, can I inverse transform it to be e to the 2t? If you can do that, the problem is done. Sounds good? That's the whole process of doing this. Of course, there's a lot of leftovers, which we will talk about next time. Okay, there's some gaps we want to add in. Number one, what is inverse Laplace transform? Okay. Every time you write down something like this, you should question yourself. Okay. E to the 2t, if you do the Laplace transform, give you 1 over s minus 2. Ly equals 1 over s minus 2. Is there a guarantee that then y is this? Not really, right? You need to ask, is L 1 to 1? If you know something, you take the derivative, that thing is 2x. Is there a guarantee that thing is x squared? Even though x squared works? No. Why? Because the answer may not be unique. Good so far? So we skip that. There is some gap here. That's number one. Number two, Laplace transform, remember, I took everything starting from 0. Why do I do that? Because when I do that, I do integration by parts. Why do integration by parts? The 0 here is actually closely related to the 0 here. Good so far? So if you think about it, I don't have a differential equation here. I have a differential equation and the initial value here. And the initial value is part of my equation because I need y0 when I do the Laplace transform. Good so far? So now if you think about it, if I don't give you the initial condition here, I give you y2 equals 400. Think about it. If I do y2 equals 400, can you use the Laplace transform before, which give you y0, which you don't know actually what y0 is? You can't do that. Good so far? So for that case, when you do Laplace transform, probably you want to do this. To make sure if you do the integration by parts, you will need y2, and you happen to have y2 here. Or in the beginning, you just shift everything back to the origin. And these two ways, you can see it's equivalent. Sounds good? Okay, so for Fourier analysis, it may be, I mean, it's not maybe, it's weird, okay? The first time I saw it, it's really weird. You said they're the same, but why? Fourier goes like this, but Laplace goes like this. Okay, the question is actually you can change this one to be 2 or -2 or whatever you want. The trouble is you need to make sure that thing matches your initial condition. And when we solve ODE, usually we give you y0. That's where everything begins, right? So that's why by convention we take 0. But really this one doesn't have to be 0. Okay. Actually you can do the Laplace transform like this. But that means what? Think about it. That means you need to know what happens at the very beginning of the universe to the negative infinity, which is not doable, right? The second thing, if you think about it, if you put everything in that way, what's going to happen to this e to the st, negative st? You were trying to add this one to help, right? Something may not be integrable, but after you smooth it down by exponential, that thing may become integrable. Good so far? If you actually start to let t to be negative, that means what? You're actually amplifying the whole signal. Because this time you're timing it with a positive exponential. So that's another thing that we want to stay away from anything other than 0. We want t to be positive. Okay, so there's a lot of subtle details here, but as far as the concern of our class, as long as you know how to calculate this, I think we're fine. Okay, when you do high-level maths, you can see you're handling something more complicated than normal sense. Okay, so everywhere you walk, you need to be aware, is there a trap, is there a trap, is there a trap, is there a trap? And I guarantee you, okay, if you do high-level mathematics or physics, the traps are everywhere. Because anything finite, we don't care. We don't give a fuck about anything finite. Anything finite? Computer. You know, nothing worth doing. Computer. We care about what happens to the infinity. We care about when we divide by 0. Okay, that's the only thing we care about. Okay. All right, that's all we have for today.